Welcome to our next video. In this video actually we will see the various secondary bonds. I think everyone have gone through the previous video which deals with the primary bonds. In primary bonds actually we have seen ionic, covalent and the metallic bonds. Okay, so what was the peculiarity is that these primary bonds share or transfer electrons among each other. Okay, and they are more strong also. In case of secondary bonds, actually no sharing or transfer of electrons is happening. Okay, let us see how the secondary bond works. In comparison to primary bonds, the secondary bonds are so weak. Okay, let us see this van der Waals forces. We can see that like van der Waals force is one of a secondary bonds, and like it can be seen at many places, like in these lizards used to stick on the walls with the help of van der Waals forces. These proteins are bonded each other with the help of van der Waals interactions, and the graphite sheets you can see in the pencils and all. Okay, smooth writing helps because graphite is a layer of carbon sheets. Okay, you can imagine like many sheets piled up over one another, and between these sheets some force are there. Okay, some weak forces are there. So those weak forces are van der Waals forces of attraction. Some polymers exhibits van der Waals forces in like polymer. These are the polymer coil, and the coil having some van der Waals forces exhibits. The water molecules exhibit some van der Waals forces. Now let us see what is a van der Waals forces. Okay, they are weak intermolecular forces. Okay, the order is the 10 kilojoule per mole or 0.1 electron volt per atom, caused by attraction between very small dipoles within the molecules. Okay, so here let us see a molecule. It consists of two atoms, or itself you can consider two molecules. Okay, these two molecules are there. One is the plus sign, and here you have the plus, and here it is the minus. The minus or the negative charge represent the accumulation of the electrons. That means in this area more electrons are, or electron rich area is here. Okay, so what will happen is that the electron rich area of this molecule will have a certain attraction with the electron deficient area of this molecule. So that attraction is known as the van der Waals forces. If you take hydrochloric acid, you can see that the chlorine is a electronegative element. That means it will take the electrons from the nearby atom. So here hydrogen is the electropositive atom. That means it will donate the electron to this chlorine. As a result, it will become a cation, and this will become a anion. So what will happen is that this anion will have a small polarity because it cannot share any electrons. So it will have a polarity. It shows a polarity towards the cation of the next molecule. So that interaction is known as van der Waals forces. Okay, in chlorine molecules also we can see this one. This is the covalent bond, and here in between you can see a London disperse force or a van der Waals forces of attraction. This represents the electrostatic potential map of a hydrochloric acid molecules. You can see that this one shows a red color. That means here electron rich is there, or the chlorine is there. So that's why some electron rich portion. So it will have a certain sort of attraction towards the blue color. Blue color means the hydrogen of the next molecule. So such bonds are known as the secondary bonds or the van der Waals forces. So in effect they are weak in comparison to the primary bonds. As the number of electrons increases, so does the size of the oscillating and induced dipoles. The size of the attractive forces between the molecules and the size of the van der Waals forces increase, which simply means that as the number of the electrons increases within any molecules, okay, what will happen? The polarity will increase. Okay, as a result, the van der Waals forces will also increase. So more number of electrons, more number of the valence electron, more will be the van der Waals forces of attraction. So like let us see the simple case of a lizard. I am here just taking just a simple case, this case only. You can see the ridges of each foot contain 500,000 hairs called setae. The foot of a lizard consists of 500,000 hairs. Okay, these are the hairs which is known as setae. End of each hair splits into between like 100 to 1000 tiny spatulas visible only with an electron microscope. Okay, this even cannot be visible under ordinary microscope, so we need the electron microscope. So this is the leg of a lizard. You can see that this is known as setae, and this at the end you can see 100 or thousands of spatulas. And what will happen is that these ultra close contact of the split ends with the wall or a floor creates billion of weak van der Waals molecular attraction. Okay, so this spatulas will create weak van der Waals forces on the wall. Altogether, this helps the lizards to stick and walk on the wall. Okay, so this is another application of the van der Waals forces. You can expect such questions for the university exams. So please read the textbook to have proper idea of such cases. So the van der Waals forces generally classified into two, or on basis of their origin. Like first thing is like it's a result of the electrostatic attraction between permanent dipoles, and second one is the result of electrostatic attraction between two temporary dipoles. Let us see two case conditions. So like the first one is the van der Waals forces from the permanent dipole. What is a permanent dipole and what's a temporary molecule? And last we discussed temporary dipoles. So here let us see, like this is the permanent dipole, are formed in asymmetric molecules where there are permanent positive and negative regions due to difference in electronegativities of the constituent elements. Okay, then one of the example is water. Okay, here what will happen for such a molecule? A asymmetry is there. Okay, it is not symmetric, and asymmetry is there. As a result, what will happen? A permanent positive and negative regions will be there. This is a water molecule, and as you all know, this is the oxygen and these are the hydrogen. And what we say, hydrogen is more electropositive or oxygen is more electronegative. As a result, it will tend to take or attract the electrons towards it. As a result, more electrons will be focusing on this region, and here we can feel a negative charge or more negative charge, and here less electron deficient area will be formed or a positive charge will be formed. So here what will happen? There is a permanent dipole is exhibited. Okay, this structure has a permanent dipole. Here negative and here a positive charge is there. Okay, that's what explained here. When the water molecule approaches another water molecule, okay, one water molecule, when it approaches another water molecule, what will happen is that a partial bond is formed between the hydrogen, positive hydrogen, and the negative oxygen. Okay, when two molecules, water molecule come close to each other, a partial bond is formed. Okay, that bond is known as the van der Waals forces, and which is formed from a permanent dipole. Okay, for this one you need to understand the concept of the permanent dipole. Okay, next is the temporary dipole. As the name suggests, the dipole is just a temporary. We cannot fix a particular portion as a constant negative charge and a constant positive charge. Okay, the temporary dipole is formed in a symmetric molecule, but which has fluctuation of charges giving rise to partial dipole moments for a few moments. Here, actually, example is the methane. Okay, here the CH bonds are like covalent bonds, and what will happen is that methane is a symmetric molecule, but when it solidifies, the bonds between the molecules are of weak van der Waals forces, and thus such a solid cannot exist for a long time. As a result, like here, some like what we say, you have what say the electrons are there, and what will happen is that sometimes some electrons will focus on one region, and another time it will move to another area. But in water molecules it is not like this. Permanently all the electrons will be focused on one area, but here it is not like that. Sometimes it will be more electrons will be like in this area, and sometimes it can shift to a new area. So as a result, because the molecule itself is a symmetric molecule, okay, so what will happen is that such since there is a variation of this electron movements within the molecule, so the bond will not be that much strong. Okay, so it cannot exist in a particular phase for a long time. That is the reason why like this property is happening. Like, let us read this one. However, weak van der Waals forces between methane molecules hold them together loosely. Okay, so this is the van der Waals forces, this dotted line. So this dotted line just hold it in a weak manner. Therefore, methane exists as a gas at room temperature and pressure. Okay, so at room temperature and pressure, what will happen is that it just exists as a gas. It cannot exist as a liquid. So if you want to bring it as a liquid, so just we want to reduce the temperature, so it will come closer and will attain that liquid state. So this is the reason. So this is the van der Waals forces developed from temporary dipole. So it's very important. So next is the hydrogen bond. Like we cannot call it as another kind of secondary bonds. It is a different type of van der Waals forces. Okay, for here for the present condition, we are just considering it as a separate bonding. Like it's a special type of van der Waals forces where hydrogen atom produce a weak bonding with other atoms. Okay, like we can say that wherever a hydrogen atom is coming, okay, that when it is creating a bond with another electronegative atom of some other molecule. Like here you can take a water as an example. Okay, water, here you have hydrogen and oxygen is there, and what will happen? This hydrogen is creating a van der Waals force of attraction with the oxygen, which is electronegative of another molecule, or another another molecule. So here the hydrogen is involved. In such a case, we can call this one as a hydrogen bonding, but it's also a van der Waals force. Now let us take the case of a chlorine molecules. Chlorine has got covalent bond, but between two molecules, between two Cl2s, there is a exhibit some force of attraction. This one is exclusively van der Waals force, but this is not a hydrogen bond. This one is hydrogen bond, as well as we can call it as a van der Waals force, but this one we cannot call it as a hydrogen bond. This is just a van der Waals force. Okay, let us see other properties. Like stronger than van der Waals forces, but compared to primary bonds, they are much weak. These hydrogen bonds are much stronger than these ordinary van der Waals forces. but in comparison to the primary bonds like metallic or what to say, metallic or some ionic bonds or covalent bonds, these hydrogen bonds are much big. So it is very important to study which why it is named like a hydrogen bond. Okay. Once again, I explain like this is a special type of van der Waals forces where hydrogen is involved. Okay, or some van der Waals forces exhibited between hydrogen atom of a molecule to the other electronegative elements like nitrogen, oxygen, or fluorine, whatever it is, of the another molecule. So such bonds are known as hydrogen bonds. Hydrogen bonds are of two types, that is intermolecular and intramolecular. Intermolecular means within the molecule some bond will be there, can form. Okay, intramolecular is that means one molecule to the another molecule. So this is the hydrogen bonding, and many significant research as well as many significant studies are there behind this one. So with this actually we are winding up the module 1. That's all for the module 1. So in this one actually we have seen what is bonding and how minimum potential energy and the forces acts on these bonds. And in the bonding, like we have seen how a primary bond like ionic bond, covalent bond, and metallic bond works, and the secondary bonds are mainly lies with this of van der Waals forces. And we have seen a special type of bond, that is van der Waals force, that is a hydrogen bonding. Okay, that's all for this video. Thank you for your attention.